Right, good afternoon. I hope you guys are all doing very well and keeping cool from the outside. My name's Dara, I work here at the National Space Centre, and I'm thrilled to be able to host this panel discussion today where we've got some University of Leicester scientists who are going to be talking us through those very first images that we got from the James Webb Space Telescope. Before we start, I'm going to say that we are going to take questions at the end, so if anything does come up, please just keep those questions with you and we'll make sure that we have some time at the end to answer any questions that you have. So first and foremost, I'd like to introduce our panel. So John, would you like to very briefly introduce yourself, please?
Okay,
You're on.
I'm live, good. I'm John Pye. I'm a senior research fellow at the University of Leicester School of Physics and Astronomy and Space Park Leicester, and I've been involved in the JWST project for more than 20 years.
Perfect. Paul, would you like to go next?
So I'm Paul O'Brien. I'm the head of astrophysics at the University of Leicester. I work on exploding stars, which we're going to study with James Webb.
And finally, Henrik.
My name is Henrik Mellin. I'm a James Webb Research Fellow, also at the University of Leicester, and I study the northern lights of Jupiter, Saturn, Uranus, and Neptune.
Perfect. So quick hands up. How many of you have heard of the James Webb Space Telescope? Perfect. So lots and lots of hands go up. Before we do get onto the images, would one of our experts like to give us a brief kind of introduction on what the telescope is and why it's such a big deal in the world of astronomy and science?
Okay, thank you. Do you have your pointer? Just in case. Just in case we need it. Okay, to give you some idea of scale first, the sun shield, which is this expanse here, is about the length of a tennis court. And the diameter of the 18-segment mirror is about 6.5 meters, and that can be compared with the 2.4 meters of the Hubble Space Telescope, which this, in some respects, is a successor to. Just in case you missed it, JWST was launched on Christmas Day, and the European Space Agency provided the launch and the rocket, and Ariane 5. It worked perfectly, and that has enabled the fuel on board JWST to be conserved to such an extent that we're hopeful for several more years of observations beyond the nominal decade or so that we were hoping for, which is great news. So a few other critical parts of the observatory. There are 18 segments in this mirror. It's segmented both for ease of construction, but also it had 3 parts, a center part and 2 folding wings, because it all had to be folded up to get inside the shroud of the rocket. Likewise, the sunshade had to be all filled up and then unfurled once it got into orbit, and that was one of the most critical and nail-biting parts of the whole space operation. Up here we have a secondary mirror, so the light, the infrared light, comes in, gets focused off the primary mirrors, hits the secondary mirror, and goes down this tube, and at the end of the tube, and behind the primary mirror, are the 4 science instruments that we'll say a bit more about in a minute or two. Below and on what we call the hot side of the observatory is the so-called Spacecraft Bus. In other words, all the electronics, the controls, etc. And you can't see it here, but just underneath are solar panels to power the spacecraft and the instruments, and it has star trackers to tell us where the spacecraft and the observatory are pointed. In terms of where it is in space, it's 1.5 million kilometers out. It's several times further out than the moon. And in this view, the sun would be directly downwards. So we always keep the sun shield between the sun and Earth and the mirrors and the science instruments, because they have to run very cold. I think
Perfect.
I'll leave it there.
Yeah, that's great. So, like John mentioned, the James Webb Space Telescope's mirror is absolutely huge, bigger than the Hubble Space Telescope's mirror, which means that it can collect more light. And the more light it collects, the more distant or fainter objects it can see. And John also mentioned that it had 4 different instruments, and they are hidden sort of behind the telescope in the instrument panel. And one of the big things about the James Webb Space Telescope is it doesn't detect visible light. It is detecting infrared light, light that is invisible to our eyes. And so its instruments are trying to detect that invisible form of light. Here are the 4 different instruments on the Webb telescope. And perhaps, John, you can give us a quick overview, and especially about the Miri instrument, of which behind John there is a model that you can come and have a look at later.
Thank you, Dara. So all the instruments are contained in a relatively small framework. There are 3 near-infrared instruments, one that is concentrated on imaging, one that does spectra. There's another one hidden somewhere called NIRIS.
NIRIS is with the FGS, so I think the 2 parts were sort of together.
Okay, yes. There's a fine guidance sensor which is for doing very accurate pointing, and as a sub part of that is another near-infrared instrument. Miri is the mid-infrared instrument, and that is the instrument that the UK has had the most to do with, and which we've been involved in designing and developing over the last 20 years or so. At Leicester, it's led by the UK Astronomy Technology Centre in Edinburgh, and also involves Airbus Space and Defence in the UK and the Rutherford Appleton Laboratory in Oxfordshire. So we'll see some examples of Miri images, and images in fact from all the instruments, and some spectra.
Perfect.
Thank you.
So again, just to sort of reinforce this idea that these different instruments are actually collecting infrared light, but of course there's a difference between our near-infrared light and our mid-infrared light. When we think about light, it has different wavelengths, and so we're collecting different wavelengths of light, and that can tell us different things about the images that we're looking at. And of course there is the spectrometer. This device or tool basically splits out light. So if you've ever taken white light and shone it through a prism, you actually see the colors of the rainbow. That's what we call a spectrum. And this instrument is doing this with infrared light. So it's splitting out that infrared light, and by analyzing that light, we can actually tell things like the temperature or perhaps the composition of different objects that we're looking at. So onto the different images. We've got a collection of some of the images here, and I'm going to leave it up to our panel to sort of guide us through the remainder of the discussion. So perhaps Paul or Henrik, do you want to pick one of the images that we might be able to discuss, and we could kind of take our discussion from there?
Okay, let's have a look at, if I can turn around so I can actually grab the thing. So if we look at the deep field for a start, I'll put the middle. That one. So this is the image that was introduced to us by the President of the United States. He picked this one as the first image. This is very similar in some senses to the images that Hubble has produced. You may have seen those amazing images, but this was taken 20 times faster than Hubble can take data. So it's just a little taster of how quickly Webb is going to explore the universe. This is a very small patch of sky. This is about the same size as if you had a grain of sand at arm's length on the sky. And that little area already contains thousands of galaxies inside it. The reason this direction was chosen was that in the middle of the region you can see these very white objects. These are galaxies in a group, or a cluster as it's called, There's a few hundred galaxies altogether, and what they're doing is acting as a lens. So just like a lens of light, you know, if you put a glass lens in front of you, it collects light from distant objects, and sometimes it'll produce a slightly distorted image depending where the object is. And if you look carefully, you can see these sort of arcs of light. There are quite a few of them once you spot them. Thanks. So there's one, for instance, and in fact, this is producing two images of the same object. So those two, and there's another two over there. And these are galaxies that are way behind the cluster. So that cluster, I'll have to quote some large numbers at you. That cluster is about 5 billion years back in time. It's about 5 billion light years away. These objects are more than twice as far away. And if you look in the background, you can see some very small, faint objects. Those are similar galaxies that are not being lensed. So that's what they would look like if the lens wasn't in the way. Was this, the gravity of this bends the light, focuses the light, and allows us to collect more light and magnifies the images. So you can see these objects in far more detail than you would have been able to just randomly. And you can see little dots around that one, for instance. You can probably see little spots of light. Those are clusters of stars in that galaxy. We'll look at a cluster in our galaxy in a bit. But those are star clusters, and we've never seen these star clusters in that much detail before. So there's a huge amount of information just in that one image. And you know, enough to keep a team of astronomers busy for years, just that one image. But that, again, that's just a small taste of what Webb is going to produce over the next decade.
I'd like to show actually something that one of our colleagues here highlighted to us, just to show how much the Webb's data actually makes a difference to our previous observations. So what I can do with this, hopefully, is to remove the Webb data, essentially, that we've collected to show you what that patch of the sky previously looked like to us. So this is, again, an infrared image taken by, I think it might have been, what is this? Unwise. So it was collecting kind of mid-infrared wavelengths. And of course, as I slowly bring up the data collected from Webb, you realize that these kind of blurry dots then actually acquire detail, and we can start seeing things that weren't even visible to us before. So when we think about, you know, what is the difference with Webb, why is it so important? It's allowing us to see things that we hadn't seen before, but also bringing into detail those things that looked blurry or not so clear to us before. I'm happy to share this link with anyone later, or you can actually take a quick look at the URL at the top. I highly recommend go away and have a play with this, because you don't even just have to look with infrared. You can change the bandwidths, you can change the sort of background, and you can look at, well, what did the optical sky look like to us? What did the visible light that we were collecting from this region look like? And how has Webb transformed that region? So I'll close that again. But I do recommend go away and have a play with that. I think that's super, super cool. John, Henrik, any comments on this image, or should we return to our kind of main gallery?
Just to say that it's quite extraordinary that the Webb can do this in such a short amount of time. And this is what the Webb was built for, detecting the earliest stars and the earliest galaxies in our universe. I think the Hubble used to go back to something like 500 million years after the Big Bang, and Webb can go back to 200 million years after the Big Bang. So we're seeing the time when the first stars ignited and when the first galaxies formed in our universe. So it's really mining our cosmic history here. And that's clearly something we're able to do. So that's super exciting. So add that. Yeah.
Okay, I'm going to return to our sort of main menu there. So we've looked at the deep field image, but of course we got a few different images from that Webb's first release. So one of our experts, would you like to pick perhaps another image?
Do Jupiter.
Of course we can. So I think I've put all the images for Jupiter on the same page here together.
So this represents the opposite end of the spectrum of that deep field. We're looking as far back in time as our technology allows in the deep field. Here we're literally exploring a cosmic backyard, right? It's planets within our own solar system. This image here This was sort of, so on Tuesday last week, or was it Wednesday? I can't remember.
I think it was the day after.
Busy week, but these images were hidden in a sort of a calibration report put out secretly on the side, and people started noticing this, like, oh my God, there's actually Jupiter data as well. And for someone who studies the giant planets, this made me really excited. So obviously, people have cleaned these up a little bit, and so we have Jupiter here in the near-infrared. Both of these are near-infrared, slightly different wavelengths. And so what we're seeing here is the banded structure, the belts of zones of Jupiter. You're seeing the iconic Great Red Spot. This is the largest storm in our solar system. It's larger than the Earth. You can fit the entirety of the Earth inside that storm. And this thing has been around for as long as we've been observing Jupiter. Galileo saw this, 300 years ago. So pretty incredible things. One thing that really intrigues me, so what I do, I study the northern lights of these planets. The northern lights happen here, around the pole here. So you can see a little spot there. Can you see it? Tiny, tiny thing, hard to see. But that's the footprint of a moon. So we have charged particles streaming from a moon entering the atmosphere right there, creating an auroral footprint. So this tells us we could actually do some great science studying the aurora of these planets, the northern lights. Another cool thing you can see, this dot here, that's a shadow of Europa, and this is Europa. So a moon of Jupiter casting a shadow on the surface, in the clouds of Jupiter. So yeah, pretty extraordinary images. We're used to seeing these kind of things from Hubble. We've been observing Jupiter with Hubble for a long time, but this being the very first images from this incredible observatory is really exciting. And we're going to get images of Saturn, of Uranus, and of Neptune as well in the coming months. So it's all kicking off. Yeah.
So super exciting. Paul and John, any comments on this, or?
Well, we could just say the length of time that image took was 75 seconds of exposure time. So the other one was 12.5 hours. So it shows the range of Webb. In fact, this is almost too bright for Webb, which is a bit of a challenge. But it shows just that Webb will be able to monitor these objects and see the changes in the planets over time, which will be really important.
Yeah. In many respects, Jupiter is too large, it's too big for James Webb to do science with, but this imaging mode works quite well, and we get these extraordinary images, so look forward to more of those. Yeah.
Sweet. And I should mention that we looked at the Webb telescope at the beginning, and John mentioned that it has a sun shield that's pointing towards the sun to protect these infrared instruments and make sure they are kept cool enough that they work. And so although we can look at the outer planets with the Webb telescope, we won't actually be able to look at the inner planets, and that's because it kind of senses its instruments are facing out into the solar system rather than actually pointing towards the sun.
But we can see Mars.
Yes. So we'll be able to see Mars as it is further out from the sun compared to the Earth. Okay, so we've looked at the images of Jupiter. We've looked at the deep field. What should we go to next?
Why don't we go to the top left, to the Carina Nebula?
Good choice.
Wow.
So this is in the southern sky, in the constellation Carina. And what we're seeing here is basically a lot of star nurseries. So a lot of areas, regions where stars are being born in dense clouds of gas and dust. We can see the dust lit up in the infrared. Thank you. Towards the lower part. And the clouds, in fact, looking very much like clouds, but they are very, very much more tenuous and rarefied than clouds on the Earth. But what we can see peering through here in the infrared, because the infrared can cut through dust and highly obscured regions, and in fact the mid-infrared can do an even better job of looking through into the depths of these stellar nurseries. So here we have the near-infrared image at the top, and the same area now in the mid-infrared, and although it's difficult to pick out in so many stars here, we are looking further into this nebula, this region of dust and gas where stars are forming. And then towards the top of the image we see this almost cliff-like structure, the edge where above that edge the dust has been cleared out by the radiation and winds of the massive stars that have formed in the region. So they've essentially blown away their own clouds in which they were formed, and we can see through now. So this is largely devoid of dust. Obviously it's still got a lot of gas around, and in fact the massive stars have and will go supernova, so they'll form another set of big explosions in the region. They'll push the gas and dust out and start to compress it, and then start to form the second generations of stars in that region. So we've got a complete cycle from star birth to star death, and then the next generation of stars. And as the generations of stars progress, we get heavier elements formed. So I think in visual terms, this is just a wonderful image. It looks almost three-dimensional in terms of the edges of the clouds.
Yeah, I've got to say, this is probably my favourite image that came out of the 5. And it's a cosmic maternity unit. This is where stars are being born. And the difference is, because Webb looks in the infrared, it can peer through this dust. When we look with visible light, the light we collect with our eyes, most of these stars will remain hidden to us. They're shrouded by these clouds, these dust clouds. But actually, by peering in the infrared, we're able to see what's happening in these clouds themselves. Perhaps one of our experts might be able to help us compare what we've seen with Hubble before compared to what we see with Webb, if I can get my mouse and cursor to go down to the right image here. So it's kind of like a comparison image here. If I actually maximize it, that might help. So what we've got on the sort of top left there is what Hubble was able to make out of this Karina Nebula region. And if we move back, we can then see what the Webb telescope was able to see. It looks very similar, our expert panel, but what difference is Webb going to make to what we can actually study and understand about these vast cloudy regions where stars are born?
Well, because we've got so much more collecting area, we can either take a similar depth of image to Hubble much faster, or more usefully, as we can see here, we can go much deeper and see much more structure because we've got better sensitivity, and be able to look further into the clouds, because unlike Hubble, we've got the mid-infrared sensitivity that Hubble lacked. And I think you can see here, though you have to be a bit careful interpreting these images, because it does depend a little bit how the person putting the false colour images together has actually interpreted the infrared light. But nevertheless, I think you can see far more structure coming out in the new Webb images compared with what was considered up to last week as being the height of sensitivity and just beautiful pictures which were coming from Hubble.
Absolutely. And I should say that this is a really striking image. And I mentioned that these are all infrared images, light that we cannot see with our eyes. So can I ask our panel a quick question? How is it that we take light that we cannot see and construct an image like this with colors that we can see? What's the process behind taking data from Webb and turning it into an image like this?
Well, let's consider it in a very simplified form in terms of a camera that you might be familiar with. So a digital camera, such as you've got on your mobile phone, has an imaging sensor behind the lens, and that sensor feeds into electronics, which is able to build up a picture. That picture can be sent to a computer. That's a similar process to what's happening here. The images get formed on board Webb and get transmitted to the ground. They're basically a set of digital photographs, just numbers. And what happens, the experts at NASA and at the Space Telescope Institute have done to create these Webb and before that Hubble images is to take the numbers and to interpret them with a great deal of intelligence and thought, converting them to colours that we can actually see, because clearly we can't see into the infrared, so they have to map that, interpret that in terms of different colours. So what has been done here is to take the different wavelengths of infrared light that Webb is seeing and cast that in terms of different colours. And there's a lot of artistry as well as science that goes into constructing these what are known as false colour images in order to give something that our brains can intuitively interpret while being nevertheless in a sense a false colour image. But the trick is to get the colour mapping sensibly, otherwise you can produce something that looks totally bizarre. But these
so
just
we
look
leave the
beautiful.
purples and the greens off and we stick to colours like reds and blues perhaps. But I guess what you're saying here is it's essentially like doing a bit of a colour by number, but what we're doing is
Yes.
making sure that the different wavelengths are assigned a different colour that we can actually interpret.
Yeah, and I think we'll perhaps see that even more represented in at least one of the other images that we're going to see.
Perfect. Okay, so let's go back to our image board. Perhaps what might be nice if we kind of follow on from there is the image of the Southern Ring Nebula. So we looked at a star-forming region, but perhaps we look at a different type of cloud of gas and dust, but this time forming from the death of a massive star. So would any of our experts like to start us off on what we're seeing here?
So we were looking a minute ago at a nebula, so that's where stars are born. This is a star, it's actually two stars in orbit around one another, and one of those stars is dying. And while it dies, it ejects a lot of gas from its atmosphere, and that's all this stuff. So over time, it's had multiple episodes of mass loss, it's called. And that material is forming this beautiful structure. It's called a planetary nebula because when they were first seen on the sky several hundred years ago, people realized they were not just points of light, they were resolved and they were colored and they looked a bit like planets. So that's why they call them planetary nebulae, but they've got nothing to do with planets. What you're looking at is this inside region, so the star is there, or at least one of the stars is there. This is the near-infrared image, which is showing the brighter of the two stars. The star that's actually ejecting all this stuff is a slightly dimmer star, which you can see in the Miri image. You can see now there are two stars. And Miri shows all this beautiful structure. So all these episodes, as the stars rotate round one another, they create structure inside this cavity. And this gas is then ejecting out at a few kilometers a second. It's not going that fast. But this gas, again, will end up in the next generation of stars. So this is similar to what the sun will do. Our own star, at the end of its life, will eject some of its outer atmosphere out into space and produce something like this. So these are very interesting objects, Planetary Nebula, and this one happens to be in the south. And we're seeing it almost down the polar axis of one of those stars. Not quite, we're a few tens of degrees off, but we're seeing into that cavity. So if you could see it from the side, you'd see something that looked like two bowls stuck together, one on top of the other, and that's this cavity blowing out into space. So they're beautiful objects. They're quite big. You can see it's about 0.25 light years, so the whole solar system would easily fit inside that cavity. All the planets that Henrik studies would be sitting inside here, so all this stuff would go straight past those planets. There's not much mass in this gas, but it's important because it's going out and will end up in the next generation of stars.
And I guess what Webb shows us here is, in much more detail, those different shells, those different layers of gas in much more detail.
Yeah, it looks a bit messy, but it's actually just because there's an orbiting system here, two stars, as well as the vagaries of mass loss. You've got the two stars orbiting, and that creates more structure. You can see these sort of filaments, and you can sometimes see regions where there's radiation coming straight out, where there's a hole in the gas inside and the radiation from the star is able to just illuminate straight out. It looks like there's a straight line, but it's just light traveling in a straight line through.
Is that what that line is up there on the top there?
That's a galaxy. Oh. Just by chance, there's an edge-on galaxy just behind the nebula. You can see it in both images, both cameras. Yeah, it confused the team when they first saw it. They thought it was just light coming out, but it isn't. You can see there's a central bulge, the central region of the galaxy. So that's an object that's probably 100 million light years away behind this nebula, outside our galaxy. And in the background, there's lots of other galaxies. So although this isn't a very long exposure, again, it's the power of Webb. So every image, basically, even some of the planetary images, are going to have galaxies in the background. So we're going to get lots of galaxies for free from Webb, even if we weren't looking. And sometimes they just cause confusion, like that object there. And there's another one.
I love that, galaxies for free, even in the images where we're not looking for galaxies. Thank you, Paul. Okay, so if we return to our kind of main menu again, I think there's a couple of images that we haven't looked at. So we can either go to Stefan's quintet, or we can have a look at the Exoplanet Spectra. What should we go to first?
Should we look at the Exoplanet Spectra?
Yeah, let's do it. I'm going to start with this slide here, Henrik, and perhaps you can use this as a sort of starting point before we actually look at the spectra.
Thanks. Right, so this James Webb basically has four pillars it was meant to do, right? It was meant to do the earliest galaxies, how do galaxies evolve, how do stars and planetary systems evolve, and fourthly, one of the things that Webb is going to do is to characterize planets around other stars. And so we do this, well, one of the ways we do that is we observe the planet go in front of its host star. And so the starlight we observe from this yellow star here goes down when the planet eclipses that star, and it comes back up as a planet leaves that disk. And so we see this signature of the changing light means that we have a planet or something orbiting this star. Now, the change in the starlight is very, very, very small. It's like parts per billion changed in the intensity of the light of this star. So it's an incredibly challenging thing to do. You can go do it from the ground, but ideally you want to do it in space with a telescope with a massive mirror and incredible sensitivity. So this allows us to characterize planets around other stars. So this is one thing we can do. We can also, instead of just looking at this sort of time versus integrated light thing, we can actually look at the spectrum. So we divide the infrared light into its constituent colors. And each element, like water, carbon dioxide, things that we associate with Earth, with life here on Earth, has its own unique fingerprint in what we call a spectrum. So if we see a distinct signal compatible with water, we can say this planet has water on it, This planet has carbon monoxide in it. So here's an example spectrum taken by the James Webb Space Telescope. So we have, again, the amounts of light blocked from the star in parts per million, and what we call wavelengths, basically the color of the light. And so we see these kind of fun bumps. If you know what you're looking at, these are fun bumps, right? So we have water here and water here. So we're actually seeing water, and I think this is one of the first times we've seen water from a planet orbiting another star. And you know, water normally means we see it in the solar system, we go, hey, there's got to be life. You know, there was water on Mars, that's why we're sending lots of stuff to Mars to explore, you know, try to find this life. Same with Enceladus, the moon of Saturn, etc. So this is really a powerful way to look at something and this spectrum tells us what it's made of. So we're going to explore a large number of planets around other stars to give us the constituents of the atmosphere. Are these atmospheres conducive for life? Probably, is my guess, yeah.
So this is probably one of the most underrated of the images, or in this case, a spectra released from Webb. So it's not a pretty image, as you might expect from a space telescope, but actually this is telling us about what we're searching for, not only in our own solar system with places like Mars, where we're looking for signs of life, but actually worlds beyond our own solar system. And it's been really difficult, right, to characterize the atmospheres of these exoplanets, these planets orbiting around other stars. I think some telescopes, maybe some like Hubble, have very tentatively tried to detect the composition of some of these atmospheres, but actually Webb is already showing us that it's going to be able to do this. And it's really important. We think about planets in our own solar system, like Venus and Mars. They actually lie in the habitable zone of our solar system. They're not too far, not too close to the sun, where if the conditions were right, they might actually be able to support life. But Venus has a really thick atmosphere and makes it inhospitable. Mars doesn't have much of an atmosphere at all. And it shows just how important atmospheres are when we're thinking about the search for life.
Yeah, absolutely. Another thing I could just add, talk about the life, something we might want to think about as well is a magnetic field. So Mars did have a magnetic field a long, long time ago, back when it had liquid water. So the magnetic field protected it from all this stuff being thrown out by the sun. But when the magnetic field of Mars turned off, basically the core solidified, the magnetic field turned off, and the entire atmosphere got washed away by the sun, by the solar wind, effectively. So another important component when we're looking for life might also be, yes, an atmosphere suitable, you know, water, all the stuff we need to sustain life here on Earth, but also probably a magnetic field to keep us safe from the stellar environment. So.
Thanks, Henrik.
Sure.
Any other comments or thoughts on the spectra here?
Well, just to say, the other thing you can see about this planet is how fast it goes around its star. So this is a planet very similar to Jupiter. Right. As we saw earlier, so Jupiter goes around the sun in about 12 years. This planet goes around its star in 3.5 days. So it's much, much closer to the star than our giant gas planet. So it's very hot. It's literally called a hot Jupiter. It's about 1,000 degrees. So if you think it's warm outside today, imagine 1,000 degrees. So it wouldn't be a nice place to live. We don't understand these planets. What are they doing that close to their star? They can't have formed there, so they must have moved somehow. They must have formed further out, similar distance to where Jupiter and Saturn are in our solar system. So all these solar systems that have been found, and there are thousands of exoplanets now, most of them do not look like our solar system. Now, it could be just we haven't tuned our methods to find solar systems like ours, or it could be that most solar systems are not like ours. And that's another influence on the search for life, because if most of these planets are much closer to their star, that might reduce the chances of them having conditions for life.
Thank you, Paul. Okay, I guess that brings us on to the final-ish image. So if we go to Stefan's quintet, we've got a compact group of galaxies here. Paul, do you want to maybe start us off on this one?
There we go. So we saw in the deep field image earlier, again, you can see getting for free all these galaxies in the background. This is probably the largest image we've seen. So this image from side to side is about a fifth the size of the moon, the full moon on the sky. It's about 6 arc minutes. There's 1,500 separate images in this image. So it's a huge amount of data. It shows what's called an interaction. So these galaxies, there's 2 there, 3, 4, these are interacting. This one just happens to be in that direction. This one's much closer to us. It's only about 40 million light years away. So this galaxy is not interacting with these guys. This galaxy looks like a normal galaxy. So this looks a bit like our galaxy would look like from the outside. You can see clusters of stars. You can see clouds of gas. Thanks. You can see, so this is a combination image. And you can see the red stuff from Miri is showing where all the cooler gas is. So those are places, again, where stars are being made in that galaxy, similar to the Karina that we saw earlier. Over here, you can see these galaxies look kind of strange. They've got all these tails wrapping around them. And that's because these galaxies have interacted. They've collided with one another. And gravity has literally pulled the stars out of the galaxies. So these are called tidal tails. So if you were living on a planet around a star in here, you'd have a very different night sky to the one we're used to. You'd see all these amazing galaxies right next to you. You'd see these plumes going through the night sky. And you'd also, if you had the right instruments, see this gas. This is molecular gas, so again, similar to Karina. This is gas that's been torn out of these galaxies and kind of shoved into the region between them. And if you look carefully, you can see this. Some of this gas is coming down this line, heading for the center of that galaxy. And what Webb discovered was that that galaxy, which has a massive black hole in the middle, is being fed this material, and it's eating that gas. And the equation that everybody knows, Einstein's E equals mc squared. Energy is mass times the speed of light squared. So mass is falling in and liberating energy. So this is what we call an active galaxy. If you look at this galaxy nearby, right in the middle, you can just see a faint dot. That's the massive black hole in that galaxy, which is not being fed much material, so it looks much dimmer, whereas this guy is just lighting up. It's a beautiful image. It looks like a crown sitting on top of the galaxy there. So this is what went on. The reason we're interested in these guys is this is what went on in the early universe. All galaxies, including our own, did this several times as they were growing. So galaxies grow by cannibalism. They eat each other, and the biggest one wins. The last one standing, as it were, is the galaxy that will survive. So these two are merging together. This one is stars being torn apart, and the one down here isn't doing so bad, but it's still showing some signs of tidal tails. You can see one there. And if you look in the background, some of the distant galaxies, you can also see that happening. There's one up there, for instance. It's a very common event in the universe. And Webb will just give us thousands of galaxies per week to look at doing this stuff. But this is a beautiful example, again, in the southern sky.
Thanks, Paul. I think a previous event, I heard one scientist talk about an image like this can produce 1,000 PhDs. Like Paul just said, there's so many galaxies in the background, each perhaps with their own different story, that there's so much to look at. And of course, this is just 5 images released from Webb, and there are plenty more to come. Any comments from the rest of our panel on this image? Okay, if not, I'm going to return to our kind of initial panel here. We've covered, I think, most of the sort of main images here. Is there anything else that our panel would like to add before we perhaps open up to some questions and answers?
Well, just to say, we've seen the first 5 images, and now the telescope is working. It's actually performing much better than we thought it would do on the ground. So that's good news. We've got 20 years worth of fuel, and so first 5 images are what's going to be many more, millions, we're hoping. Yeah.
Perfect. Well, thank you very much to our panel. Can we just very quickly give them a round of applause? And I think I'm going to run around with the microphone. So if anyone has any questions they'd like to ask, if you pop your hand up, I'll bring the mic around. Don't be shy. There we go.
Who gets to decide what the next target is?
Well, the observing time is allocated. It's done what's called a double-blind system. So the people who apply, their names are on the proposals, but those names are removed. So the panel doesn't know who is applying to try and remove a bias. And they also, the panel, when they rank the proposals at the end, they don't know. Only later on is it revealed. So the people who get observing time, and the three of us are lucky enough to have observing time, it's done in a very careful way because time is very precious. You know, it's heavily oversubscribed. There are maybe 10 times more people want to use it than can use it. But we've got 20 years, so if you don't get time in the first year, just try again.
Fingers crossed then.
Any other questions?
Is the space infinite?
Space is not infinite. The universe started in what's called the Big Bang. And one of the things we want Webb to discover is when were the very first stars made. So the Big Bang happened about nearly 14 billion years ago. And the first stars were formed a few 100 million years after that. Hubble isn't capable, the Hubble telescope isn't capable of finding those stars. Webb is capable. And in fact, in the deep field image, there are already galaxies that have been identified that are within about 800 million years of the Big Bang. And that's from a very short exposure for Webb, relatively. So if we push a bit more, we should find those very first stars.
Thank you. What a great question.
You've explained a little bit about how the information is interpreted so that we can kind of understand it when we see pictures that we can understand. But how does it send that information? Like, what's the process? How does it send it to us? It's so far away, and what form does it arrive in? Is it pictures, or sometimes is it numbers? Is it what? How does it reach us?
Okay, let me take you through the data flow, as it were. So that gives me the opportunity to introduce my Lego model here. So this is one I built earlier. So you can see, so the light from the galaxy or the star hits the mirror, the primary mirror, secondary mirror, disappears into the back. In the back is where the science instruments are. The cables from the science instruments electronics feed through down here to the area known as the Spacecraft Bus, which is where the main spacecraft electronics is, and that contains transmitters and processing computers, which reformats the data. It's like data in any computer. And then the transmitter, there is a high gain antenna here, which has to point at the direction of the Earth. So it doesn't do that continuously, but there are several downloads each day because the data volumes are quite large, and that if we don't download at least twice a day, then the onboard store would get filled up. So the data gets downlinked to one or more large dish ground stations run by NASA, and from there eventually it finds its way to the Space Telescope Science Institute in Baltimore, Maryland, on the east coast of the USA near Washington, and they're charged by NASA with both operating Webb and in fact Hubble as well, So they have very large computers and a lot of storage, computer storage space where the data ends up, and it then goes through a number of what are called calibration pipelines. These are just sets of computer programs all chained together, and you put the data, the raw data as it were, in at the beginning. The software performs various calibrations. In other words, the instruments both on the ground and in orbit have had their characteristics calibrated so that we know exactly how sensitive the mirrors are and how sensitive the instruments are, and can take out the various distortions inherent in the system. And at the back end, the output of these pipelines are corrected images, basically in the same sort of format that you get from your mobile phone camera or any other digital camera, a set of ones and zeros, which can then be interpreted either as these beautiful color maps, or if we know in what we're looking at, we can often interpret these colors, if you like, in terms of different temperatures in objects or different compositions. Does that basically answer the question?
Any other questions?
Good afternoon. This is a visitor's announcement.
Just hold on 1 minute while this announcement happens, then you can say your question.
Closing 40 minutes time at 4 p.m. That's the Rocket Tower closing in 40 minutes at 4 p.m. The rest of the set will close at 5 p.m. Thank you very much.
Why is the James Webb Telescope called the James Webb Telescope?
Why is the James Webb Telescope called the James Webb Telescope? That's a very good question. James Webb was, I think, the second, certainly one of the early heads of the US NASA organization. He was responsible for NASA in the 1960s during the Apollo moon program, but he was also very much in favor of space telescopes. So that's the origin of that name.
Brilliant. Any other questions? If not, I'm going to ask one question. We've talked about Webb and we've said how much it will help us discover that we haven't before. And I guess this is more personal, perhaps, to the research that you're doing. What are you hoping that Webb will help discover or find out that we don't quite know yet? And that's to anyone.
Right, should I start? Well, I think generally I'm super excited about everything. Like all these images we've seen last week, they're all mind-blowing. So I'm all for more of that. On a personal level, talk about the aurora of the giant planets. We've never seen it on Neptune, never. And so this is the way to do it. The most sensitive telescope ever built, I think. It would be awesome to see it. We have no idea what it looks like, so it will be a completely new discovery. Thank you.
Sounds exciting.
Yeah, so one of the things I want to study is where the heaviest elements come from. So the mirrors of Webb are coated with gold, for instance. We don't really understand where things like gold, platinum, those heavy elements are formed. You might think all elements are formed in stars, inside stars, but that's actually not true. The biggest stars even struggle to form those very heaviest elements. And of course, everyone's interested in where gold is formed. We think we have a clue. There's an object called a kilonova, which Webb hasn't looked at yet. The problem with kilonovae is they are made all of a sudden. They're made by merging two neutron stars. So we've got telescope time, but we don't know when to carry out the observation. We have to wait for the universe to make one. And then we need another telescope to find it. And then we can point Webb. So it might be in next month. It might be next year. We don't know. And one of the things that occurred to me the other day, of course, is Webb's mirrors being coated in gold. We can use those mirrors to find where gold comes from. So it's a kind of full circle moment there.
That sounds super exciting, and I hope, within the next few years we actually have something.
Okay, I'm involved in some of the deepest surveys with Webb, so I'm hoping to see beyond Hubble and see some of the first stars and galaxies to form. But they will be very challenging observations because we'll be working right near the limits of even Webb, and even with 50-hour observations.
But you'll be teetering back as far back as possible, I guess.
Yes.
Sounds good. All right. If there are no further questions, I think we're going to call to wraps our panel discussion there. I want to say a massive thank you to everyone who's been here asking questions and also listening intently to our expert panel. I'd like to say thank you to all of you for attending today and giving us this insight. Before everyone leaves, I'm just going to leave out some stickers and some booklets. So if anyone wants to know a little bit more about Webb, I'll leave them on the front stool there. Please do collect one before you leave. And if not, enjoy the rest of your day here at the National Space Centre. And just before we go, please let's give our expert panel another round of applause.